Hello everyone, welcome to my channel. Please like and subscribe. In this video, we'll be learning how to design a beam for single reinforced section. Our problem is that a simple supported rectangular beam as shown below carries a dead load of 3.76 kN per meter, excluding self-weight of the beam, and imposed load of 10 kN per meter. We are required to design the beam if reinforcement strength is 460 Newton per millimeter square, concrete strength is 30 Newton per millimeter square, and the density of concrete is 24 kilonewton per meter cube. We have given this beam, which is simply supported of this span, and it have a cross section of this dimension. So, for the designing of this beam, the first step is to determine the effective span of this beam. And since this beam carries a dead load excluding self-weight, so it will be required to determine the self-weight of this beam. After that, we'll add the dead load which was given so as to obtain the total dead load to be used for the design. Now let's solve step by step. The first step is to determine the effective span. Effective span of this beam. This beam it was drawn this way, which was supported by two supports. Of this span. Here was 100, and this is 6900 millimeter, and this is the center of the support. So it will be this is length of center to center span, and this is the distance from the inner face of the support is called the clear span. This is the clear span of this between two supports. So to determine effective span for simply supported beam, effective span for simply supported beam is obtained by taking the length of center to center span, which is obtained by taking clear span, which is 6900 plus the distance from the center of this support to the inner face. So to obtain the distance from the center of this support to the inner face, it will be obtained by taking width of the supports divided by 2, and the width of these supports divided by 2, which is 100 divided by 2. The result will be 7,000 millimeter, which is equal to 70 meter. Or by taking clear span plus effective depth. Effective depth is from the center of this tensile steel up to the top. So clear span plus effective depth. Clear span of this between two supports is 6900 plus effective depth of this. Effective depth of this beam is 400, which makes the result of 7300 millimeter, which is equal to 7.3 meter. So to obtain effective span of this beam, it will be obtained by taking the less among of these two. So 7 meter is less than this one, so 7 meter is equal to the effective span. Therefore, effective span of this beam is 7 meter because it is less than 7.3 meter. This effective span, it will be used in our design calculation. 7 meter effective span. The next step is to determine design load. Design load. Design load as per BS is given by 1.4 times total dead load plus 1.6 times imposed load. Total dead load. To obtain total dead load, since beam carries a dead load excluding self weight. So to obtain total dead load, it will be equal to self weight plus dead load, which was provided. It was 3.76 kilonewton per meter. So self weight of this beam is obtained by taking area of the section of the beam, times density of concrete. This area of the section is obtained by taking the overall depth of this section times the breadth of the section. So it will be equal times breadth times overall depth of the section times density of concrete. Self weight of the beam, it will be equal to breadth. Breadth is this one, 300 times overall depth of the beam is this one, 450 times density of concrete, which is 24 kilonewton per meter cube. So to obtain in kilonewton, since the breadth and the overall depth are in millimeters, so to make it in a meter, we multiply by 10⁻⁶, so as to obtain in kilonewton per meter. Now 300 times 4 times 24 times exponent -6 is equal to 3.24 kilonewton per meter. Therefore, the self weight of this beam is 3.24 kilonewton per meter. Now, this to obtain total dead load, it will be equal to self weight, which is 3.24 plus dead load, which was provided in a problem, which was 3.76. It makes a total of 7 kilonewton per meter. This is a total dead load to be used in our design calculation. And the imposed load from a problem is 10 kilonewton per meter. Now, to obtain the design load, it will be 4 times 4 imposed load times dead load 1.6 imposed load. Design load, it will be equal to 1.4 times 7 plus 1.6 times imposed load, which is 10. Now design load, it will be equal to 1.4 times 7 plus 1.6 times 10. It will be equal to 25.8 kilonewton per meter. This is a design load which will be used in our design calculation. Now the next step, design load, we have obtained 25.8 kilonewton per meter. So the next step is to determine the maximum design moment to be used. Maximum design moment for simple supported beam is given by NL square divided by 8. NL, which is design load, is 25.8 times L, which is 7 square divided by 8 times 7 square divided by 8. The maximum design moment maximum design moment is 158.03 kilonewton per meter. The next step is to determine ultimate moment of resistance. Ultimate moment of resistance. Ultimate moment of resistance. M1. Ultimate moment of resistance is given by 0.156 SU BD square. Now, ultimate moment of resistance, in our problem where we are given SU, which is concrete strength, was 30. So, ultimate moment of resistance will be 0.156 times SU, which is 30, times Blitz. Blitz of this section, of this beam section, is 300 times effective depth, which is this one, which is 400 square. So to make it in kilonewton per meter, in kilonewton a meter, we multiply by -6 because SU beats and depths are in millimeter. That's why we multiply by power -6. Therefore, ultimate moment of resistance 0.156 times 30 times 300 times 4 square, 400 square times 6.6. It will be equal to 224.64 kilonewton meter. Now, the next step is to determine we check the section adequacy. Does it for single reinforced section or double reinforced section? If because the maximum design moment is 158.03 kilonewton meter is less than 224.64 kilonewton meter. Since maximum design moment is less than ultimate moment of resistance, hence no compression reinforcements, no compression reinforcements required. Therefore, we design as a single reinforced section. But if the maximum design moment would be greater than ultimate moment of resistance, normally we design as a double reinforced section. In our problem, maximum design moment is less than ultimate moment of resistance, so implies that no compression reinforcement required. That's why we design as a single reinforced section. Now, single reinforced section, it have only tensile steel which is provided at the bottom of the section. So to determine the area of tensile steel is given by maximum design moment divided by 0.95 Fy times Z. This is normally used when partial factor is 1.05 as per BS at 110 part 1 1997. But Z is obtained by taking effective depth times 0.5 plus 0.25 minus K over 0.9. under root. This should be less than or equal to 0.95 times effective depth. But this K is obtained by taking maximum design moment divided by 0.9 divided by FCU BD square. K is equal to maximum design moment divided by FCU BD square. Maximum design moment was 158.03 kilonewton meter. So to make it in Newton per millimeter square, we multiply by power -6 divided by FCU. FCU is 30 times Brits, which was 300 times Brits, which is effective depth, which is 400 square. K will be equal to 158.03 x.6 divided by 30 times 300 times 400 square. K will be equal to 0.1097. To obtain Z, it will be equal to effective depth times 0.5 plus 0.25 minus 0.1097 over 0.9 under root. Z, this should be less than or equal to 0.95 times effective depth. So divided by 0.25 minus under root of 1 plus 0.5. It will be equal to 0.86 times effective depth. This is less than 0.95 times effective depth. Therefore, Z it will be equal to 0.86 times effective depth, which is 400. Effective depth is this one. Effective depth is this one, 400. The distance from the center of this area of tensile to the top. So it will be equal to 0.86 times 400 is equal to 354 millimeter. This is Z, 354 millimeter. Now, area of tensile steel. Area of tensile steel it will be equal to maximum design moment divided by 0.95 FYZ. Fy is reinforcement strength. So maximum design moment is 158.03 power 6 Newton per millimeter square over 0.95 times Fy. Reinforcement strength was 460 Newton per millimeter square times Z, which is 354. Area of tensile steel is equal to 158.03 x.6 divided by 0.95 times 460 times 3 of 40 will be equal to 1050.23 millimeter square. This is the area required for the tensile steel. So the next step is to determine the number of bars required. The number of bars required for the tensile steel. Number of bars, but one bars is equal to pi times diameter of bars squared divided by 4. The size of diameter for beam starts from bar diameter starts from 16 millimeter, 20 millimeter, 25 millimeter, and so on. But let's assume our bar diameter is 20 millimeter. Now one bars it will provide pi times 20 square divided by 4. Divided by 4, it will be equal to 314.6 millimeter square. This is the area of one bus. The area of one bus. One bar provides the area of 314.6 millimeter square. Now, to obtain the bars required for the steel, it will be equal to area required, which was 105.2 over 314.16. It will be equal to, divided by 314. It will be equal to 3.3. So the bars required, it will be equal to, for economical use, it will be equal to 4. It should be rounded. It will be equal to 4 bars with a diameter of 20. The next step is to draw the detailing of this beam. Okay, before detailing, we are supposed to determine the areas required for the steel. The areas required. Area required is obtained by taking number of bars, which is 4, times the area of one bar, which is 314.16. So 4 times 3.41.16, it will be equal to area required. Area required for the design is 1256.46, which is equal to 1257 millimeter square. It should be rounded so as to be the whole number. Therefore, the next step is to detailing of reinforcement. It will be drawn in this way. The section of the beam. We know area of tensile is in our designing. We was designing as a single reinforced section. Single reinforced section. Only tension reinforcement is provided, and this tension reinforcement is provided at the bottom. In our design, we have obtained 4 bars, so it will be provided at the bottom. We provide 4 bars with a diameter of 20. 4 bars. We provide at the bottom. This is 4 bars with a diameter of 20. This is tensile strength. Tensile strength, and the distance from the center of this bars up to the top is effective depth, which was 400, and this is overall depth of the cross section, which was 450 millimeter, and the width was 300. So this is 4 with diameter of 20. It provides the area of tensile, which is equal to 1257 millimeter square. Thank you for watching this video. If you found help in this video, please like and subscribe for more civil engineering contents.